on Thursday, start to introduce to you complex numbers, graphing complex numbers, and explaining that complex numbers are a rectangular coordinate system, and the process of graphing what we call an Argand diagram uses rectangular motion. And if we think about what we've done already in the Cartesian plane, if there's something that's rectangular, then chances are we can convert it into more of a trigonometric or polar version. So that's kind of what we were messing around with towards the end of the period on Thursday. But I want to kind of reiterate some of the things that we talked about then. First thing here is if I've got this point 3 plus 4i. And I'm just going to draw mostly the first quadrant here. Give myself a little bit of room to write other things. If I go 3 plus 4, what we talked about on Thursday was if I want to graph this number, it has two components. Okay? It's different than working with like graphing just 3, or graphing just 4, or graphing pi, or radical 7, or 12, or negative 50. When I just have a real number that I want to graph, I only need a one-dimensional number line. Okay? Either that horizontal one or that vertical one, doesn't matter. But now 3 plus 4i, so that one horizontal, one-dimensional number line can address the 3, but it doesn't do anything for the 4i, right? So I need to have something to be able to mess around with that 4i. So what we do, and what's I think very interesting with this stuff, is that it plays into all our other mathematics and works exceptionally well with all of our other mathematics, is that we introduce this additional axis, basically taking the y-axis away and putting it as an imaginary axis. Okay? And now we're going to take 3 plus 4i, and we're going to graph that, kind of like the 3 is our horizontal distance, and the 4i is our vertical distance. Okay? So it's very, very similar to how we graph points in the Cartesian plane. I'm going to move over 3 units, and then so that addresses the real part of 3, and then I'll go up 4. And that addresses the imaginary part, 4i. So we call that point z. Okay? That's z is equal to 3 plus 4i. And here's the thing. This is that was moving rectangularly, right? Moving left and right, up and down. So when I moved right and then up, I created a right angle there. And that's the idea of having rectangular motion or movements. So I moved right. That distance, I'm just call that A right now. And then I moved up, and I'll call that value B. Okay? Now, if we make the connection between what we've already done in the Cartesian plane, is that I should be able to go from 0, 0 to get to z, which is 3 plus 4i, I should be able to do an alternative way. I should be able to move along that blue radius, okay, at a particular angle. Okay, so this blue radius, that right there, we're going to call that, it's referred to as this. We say it's the absolute value of z, which we call the modulus, okay, is equal to the square root of a squared plus b squared. In our specific situation, a was 3 and b is 4. So it should give me the modulus to be 5, right? Now, the modulus is consistent with being the radius of some particular circle. So our r, in this particular case, is 5. Okay? So what we're saying here then is that 3 plus 4i is on some circle of radius 5. Does that make sense? Okay. Now what we're interested in is figuring out, well, what exactly is the direction to get to that 3 plus 4i. And the direction is ultimately defined by that angle theta. Okay? And that angle theta is going to be found, just like we did in the Cartesian plane. It is the tangent inverse of b over a. In the Cartesian plane, we did y over x, right? Okay? But it's going to be tangent inverse, in this case, of 4 divided by 3. And that ends up giving 53.13 degrees. So, what we end up with here, guys, is now two pieces of information, a radius of 5 and an angle of 53.13 degrees that we can travel along or use in tandem with one another to travel along that blue distance, that blue segment, to get to the same exact point Z. Okay? Now, what we have to be able to do is have an understanding of what A was. Okay? So if I look at this information here, this is A, this is B, this is R. Does it make sense that A is related to R through that formula right there? Cosine of theta is adjacent divided by hypotenuse, right? Well, doesn't R cosine theta then equal A? That make sense? Now, I should be able to do something similar up here with R and B. Okay? The sine of theta is equal to B divided by R. So B then ends up being R sine theta. Now, why would I want to know those things? If I remember what A and B were, A and B, that's something like A plus BI. That was the 3 and the 4, right? Okay. Now what we just developed here are formulas that are going to allow us to transition from A to something that involves this R and this theta. A is now R cosine theta. So A is R cosine theta. B is going to allow me to transition from this 4I to now something that involves the R and the theta that we use. So this B becomes R sine of theta. Okay? Now, there's also this I here. We'll put it right there for now. But when we do this, remember that theta is the argument. I is not part of the argument. Okay? So right now we're going from the A plus BI was a rectangular coordinate. Okay? When we rewrite it as R cosine theta plus R sine theta I, that is now a polar form of that complex number. Okay? Or sometimes referred to as a trigonometric form. Okay? That's kind of a, I don't know if we've used that word yet with dealing with polar coordinates. Sometimes they're called trigonometric coordinates. Okay, instead of just polar. Okay, so this is nice. Okay, that is the polar form of a complex number, but there's some stuff that we can do to make it a little bit more concise. Do they both have R in them? Okay, so what we do is we factor that R out, and that's going to give us R times in the quantity cosine theta plus sine theta. Now, I could put my I out here at the end, right? But when I do that, there's confusion, especially if people don't write the parentheses around their argument theta. There's confusion of whether that I should be part of my argument or if it should be outside. Does that make sense? So really the idea is, does it belong there or does it belong there? And that's actually the way it belongs. The I needs to be on the outside. So to eliminate that confusion, we use the commutative property and we put I right there. Okay? And that is the kind of the preferred way that WebAssign is going to ask you to rewrite your rectangular complex numbers as in regards to their polar form. But there's a way that we write it by hand, and the way that I'm going to verbalize this a lot quicker, a lot more efficiently. Basically what they do is they take come on. There we go. We take that value there, write that down. Then we take that value, or that letter right there. So we start to kind of develop an acronym here. So we take C, and write that down, it stands for cosine. Then we go to the I, and we write that I down. Obviously it stands for the imaginary part. And then we write S for sine, and then we pick off the theta. And we write that red thing as this. We read R cis theta. R cis theta. And that's a more concise way of writing this thing in red. Now, with that process or that procedure of writing it more concisely, I think we lose a little bit of understanding, a little bit of context. Does that make sense? This is a little bit more vague than what this is. We need to realize that when I expand cis into cosine theta, it's cosine theta plus I sine theta. Does that make sense? When I write it this way, I don't see that plus in there, right? And I don't see that I is stuck to sine. Written in this way, maybe somebody could argue that I is stuck to cosine. So we got to make sure we understand that link. But what that's going to lead us to, we're going to see here in a little bit with some examples towards the end of the class, is that is going to clean up a lot of our kind of rectangular algebra that we do. Okay, so this is going to be a really nice thing for us if we can convert rectangular complex numbers to polar. All right, so that's kind of what we ended with on Thursday. All right, so let's just kind of pick up and do some examples with this information. See some links between different formats. Maybe we'll jump back and forth between this and GeoGebra and graphing these. Desmos doesn't have a native complex number grapher, meaning that I can't just type in 1 plus I on Desmos and it graphs for me. GeoGebra actually does. So that's what we're going to use to show some of this stuff. When we're doing these, when you're changing things to polar form, you don't always need a picture, especially if you're really cognizant of what quadrant you're in and all that kind of stuff. You don't necessarily need a picture, but a picture is not a bad idea, especially the first couple times we do these. So I'm going to graph 1 plus I. Okay? So here's my real axis. Here's my imaginary axis. I go 1 over in the real. I go 1 up in the imaginary. And that point right there is 1 plus I. Okay? We want to convert that into polar. Okay? So into polar form, it says that we need to be able to write something as R cosine of theta plus I sine of theta. So with this information, we need to come up with what R is and what theta is. So that distance right there is your R, correct? Well, that is the hypotenuse of a 1 by 1 right triangle. Okay, now I'm going to use special right triangles to figure out that R, or what we refer to as the modulus of this complex number. The modulus of Z is radical 2, so that's R. R equals radical 2. Now I'm going to find theta. Now again, we could probably use our special right triangle stuff to find theta a little bit easier than using tangent inverse. Okay? Either way is fine. If that's 1 and that's 1, that's the special right triangle. What kind of special right triangle is that? 45, 45, 90, right? So that's what theta is. Okay? Or Obviously if I wanted to go r is equal to a squared plus b squared, that gives me radical 2 there. And if I want to say theta was equal to tangent inverse of 1 over 1, that gives me 45 degrees as well, right? Okay, so those are all kind of approaches. I think we're at a point, if we see special right triangles, we should probably be able to use those because they do just quicken the process. So now, if I want to write this thing here, so z equals 1 plus I, that's rectangular form. If I rewrite that as z equals r, which is radical 2, times cosine of 45, plus I sine of 45. That is polar form. Okay, now this is still, I think that's a pain in the butt to write. It's what we have to use to type stuff into GeoGebra. But for all the things that we're going to do by hand, this makes it a little bit more convenient. Okay, write it as radical 2 cis 45. Okay, knowing that that is kind of the condensed version of cosine 45 plus I sine of 45. That's what cis stands for. Okay, so let's kind of look at this. Let's analyze this with a picture in GeoGebra. If we, in GeoGebra, all we've got to do is type in 1 plus I. Okay, it knows that I and you kind of see that it gives a weird, I don't know if we can zoom in, but the dot on I is kind of weird. Okay, if you can really look in on that or zoom in on it. It's basically telling us that GeoGebra has a native built-in understanding for what we mean when we say I. If we type in I on Desmos, it asks us to create a slider, and it assumes that I is just a normal variable. Okay, so that's the issue with Desmos. We can maybe program it a little bit with certain sliders and stuff like that to get to it, but this is just so much easier. It's already built into GeoGebra. So we have 1 plus I. That's the rectangular form. Think about this. Is that point right there on that ray right there divides the first quadrant in half? So that's a 45-degree angle, right? Okay. And if I want to be able to figure out how to get there, well, that's the, if I go from A to Z1, that is the diagonal of a 1 by 1 square, which is radical 2. Okay. So when we go ahead and rewrite this as square root of 2, now this does not have a CIS command or a sys command. You actually have to type in times cosine 45 plus I times sine of 45. And now if you're going to use this, I have to put that multiplication there with I, because if I do this, it doesn't know that I mean the implied multiplication. Does that make sense? So you got to put times sine. But if I graph that, we see, I don't know what that's all about. What's happened? All right, so that point right there, see if I change the color of it, is the same point as Z1, right? Does that make sense? Now, if I double click on this, that's the version that's being graphed. GeoGebra just does a good job of being able to convert that to a rectangular system for us. Okay? And I don't think, if there's alternative versions for something, you can sometimes right click on the object and there'll be like two phrases here. Sometimes it'll say complex number Z1, but then it might say underneath it like polar form of Z1. You might be able to click on that, but this concept doesn't allow me to do that. But we do see that what we've typed in R cis theta is the same thing as what we typed in rectangular form. Does that make sense? Okay, so that's kind of a way of maybe verifying what you have done. Let's do B and C here. We've already done D. We did D. That was kind of our first one we did. If I do B, okay, now this is the reason why I think a picture is not necessary, but by all means is useful when you go through this process, because if I don't have the picture, I might use the wrong theta. So -1 plus root 3, -1 plus root 3. So I'm going to go over on my real axis, -1. I'll go up on my imaginary axis, root 3. Root 3 is about 1.7. So there's Z equaling -1 plus root 3 times I. Okay. Now if I want to find R, which is that distance right there, correct? R, we said, and here's the logic of, we don't necessarily need a picture because R was defined as being the square root of A squared plus B squared. Well, there's your A, there's your B. So I don't need a picture to help me find R. A squared would be 1, root 3 squared would be just 3, so that gives me 2, right? So my R value, this point, -1 plus root 3I, is existing on a circle with a radius of 2. Okay? Now here's where a picture can come in handy for us. Or at least if I don't draw the picture, still being able to visualize it in my mind by knowing what quadrant I'm in. Because when I take and try to find theta with this right triangle here, this is radical 3, this is -1. When I find theta, which is right there, we're going to say theta is equal to tangent inverse of B over A. That's what the formula is for finding theta. If you go back to rectangular form with the Cartesian plane, it was y over x, right? But now our y-axis is the imaginary component, which is B, and our x-axis is our real component, which is A. That's the same procedure as what we've been doing. Now, if I evaluate that, tangent inverse of radical 3 is 60. So tangent inverse of negative radical 3, because of how the tangent works with even and odd functions, this ends up giving me -60 degrees back for theta. Okay? And this is where we need to pay attention to what quadrant we're in. This is why the picture would be beneficial, I think. When we talk about theta, we don't want the -60 degrees. We don't want positive 60 degrees either. Theta for us, remember, it's a direction from how you go from that axis right there to that vector right there. So theta that we're really interested in, that shows up in our R-cis theta, is that right there. Does that make sense? So how big would that be? Say again? 120. So 120 degrees is the theta that we're interested in when we type it into R-cis theta. So R, we said was 2. We can go cosine of 120 plus I sine of 120. Or what I'm going to eventually start doing is just writing it as 2 cis 120. That's obviously a lot more efficient, a lot quicker to write. Now, here's one thing that somebody in the last class asked. They said, well, when I write that as radical 2 cosine of 120, I sine of 120, do they want us to go and simplify that cosine of 120? Well, think about this. What is the cosine of 120? Think about where 120 is. It's about right there, right? So is the x value 1/2 or radical 3 over 2? It's 1/2. And it's going to be -1. So that thing goes to -1/2. So sine of 120 is radical 3 over 2. I got that I there, right? What's 2 times -1/2? -1. And then 2 times radical 3 over 2 gives me just radical 3 times the I gives me that, right? So if I did kind of simplify this with the cosine of 120, it's going to get me back to the rectangular form that we started with. Does that make sense? And that could be maybe a check to say, you know, have I done things right? Do I have the correct r cis theta? We'll go one more step, evaluate it, and see if it gives you back what you started with. Okay? So that's an option. Now, going to GeoGebra, another reason, again, the picture I think is useful. If we had -1 plus square root of 3i, that point there, and we write then the square root of, I mean, we have square root is 2, right? 2 times cosine of 120 plus I times sine of 120. Obviously, it puts that point right on top of Z1, right? Okay. Now, if I would have kept this at 60 degrees, because, or maybe even -60 degrees, because that's what my calculator spit back to me. So that's -60, and this one is -60. See that it puts me here in the 4th quadrant? Okay. Now, there is a relationship between that point and that point, and we'll talk about that here in a little bit, a couple days. But if I solely depend on this formula for tangent inverse finding theta in my calculator and not paying attention to what quadrant I'm in, I'm probably going to get the wrong theta. Does that make sense? And then if I get the wrong theta, obviously, then I don't convert into the correct polar form. All right? And basically what that's going to do, if I use the wrong theta, it's going to mess up that sign and that plus sign, okay, in various ways. All right? Okay? So that's how we go from polar to rectangular, rectangular to polar. Let's do one more real quick here. And this is the idea. As you do enough of these, I want to kind of go through this a fast way here without maybe drawing a picture. So R should end up being the square root of that squared plus that squared, right? Well, if I square 4, I get 16, right? Square root radical 3, and you get 3, right? 16 times 3 is 48. So that's what I get when I square that. When I square that, I get 16. That gives me radical 64, which is just 8, right? Okay. Now, theta is tangent inverse of B over A. So it's going to be tangent inverse. Okay, B is -4 over A, which is -4 root 3. So it gives me tangent inverse. I'm going to write it this way. It's 1 over root 3, right? And if I rationalize that, it's root 3 over 3. And a lot of times, especially when we're starting off with these processes kind of for the first time, they're going to give you values of A and B a lot of times that work out to be really nice. And when I go tangent inverse, I get things like 1 or root 3 or root 3 over 3, because root 3 over 3 attaches itself to what angle? 30 degrees. Okay. So now I've got R and I've got theta, right? But look at this. What quadrant is that really in? 3rd quadrant, right? Okay. So visualizing that that's a 3rd quadrant angle, and I've got 30 degrees, what do I really need to do that 30 degrees to put it in the 3rd quadrant? Add 180 to it. So the theta that I'm really interested in here is 210. Okay. Picture-wise, for those of you that are kind of missing out without the picture, -4 root 3 would be over here. -4 would be maybe, just to scale, maybe it's right there. So that R right there is 8. And the theta we just found was that angle right there. Does that make sense? Like Emily said, then we got to take and add 180 to it to get from the polar axis, or the positive real axis, to that r. Okay, so theta is really 2 10. So then this in polar form is 8 cis 210 degrees, and that's what we're looking at. Okay, so the hope is, because what I'm about to show you here in a minute is supposed to like expedite the process of multiplying complex numbers. But in regards to doing that, you first have to take your two complex numbers that you're going to multiply together and convert them into polar form. Okay? Well, the argument is, well, that's going to take a long time. It shouldn't if you don't have to draw the picture. Okay? If you can take square A and B and add those together, and then take the tangent inverse of B over A, you should be able to convert a rectangular complex number into polar complex number very quickly. Okay? So here's the idea, and this is not the key theorem that we're going to be interested in this section, but it sets the foundation for it. Okay, the key theorem that we're usually interested in is called de Moivre's theorem, which talks about taking like z1 and squaring it, and then cubing it, and then there's a fourth power and fifth power and sixth power, raising some complex number to a large power. This is kind of a more maybe involved aspect of that, because this is taking two complex numbers that are maybe the same or completely different and multiplying them. The Moivre's theorem kind of talks about them z1 and z2 actually being the same point. Okay, so we'll get to the Moivre's tomorrow. But this says if two complex numbers z1 and z2 have these polar forms, where z1 is equal to r sub 1 cosine theta sub 1 plus I sine theta 1. Or, if you want to write it this way, r1 cis theta 1. And those subscripts are just identifiers. I think subscripts a lot of times confuse people. They make you, I don't know, get worried or anxious about the math that's going on here. They're just identifiers most of the time. Okay? They're just telling you that r sub 1 is the r value, the radius that came from z1, or the first point, right? And then r2 is the radius that came from the second point. Okay? They're just identifiers or ways for us to link which radius comes from which point. Same thing for the thetas. Okay? I think, at least when I was in physics, you started seeing those things with forces. You saw subscripts and then superscripts and all that kind of stuff. And it looks, you start seeing stuff like this. Well, that looks crazy and stupid to me. Okay, but if you just understand what these are identifiers. Maybe that's something that I got to square. But the subscript is usually an identifier. All right. So what this is saying is, if I have these 2 points in polar form, I want to multiply them together. I'll take z1 times z2. All I have to do is multiply the radiuses and then add the thetas. Okay? So multiplication in this form would look like r1, r2, cis theta 1 plus theta 2 if you write it in the condensed version. And that is usually a much quicker way of multiplying two complex numbers. Okay? Now, dividing them is the same idea, but instead of multiplying the radiuses, we divide them. And instead of adding the arguments, we subtract them. Now, here's what's important, is that I have to pay attention to the order that we divide. If I want z2 over z1, that's going to be r2 over r1, right? And then it'll be cis. Now, is subtraction commutative? No. So because I went r2 divided by r1, this needs to be theta 2 minus theta 1. Does that make sense? So when you're going to divide, pay attention to what your numerator is and what your denominator is. It's always going to be, when I look at my argument, it's the numerator minus the denominator. Okay, so that's something to pay attention to. Okay, so let's see how this kind of all works out with us. And obviously, when I want to divide two complex numbers, the bottom number cannot be 0. Okay? 0 is a complex number, 0 plus 0i, but we obviously can't divide by 0. Okay? So in kind of layman's terms, it basically says if I want to multiply two complex numbers, you multiply the moduli and you add the arguments. To divide the complex numbers, you divide the moduli and you subtract the arguments. Just remember, order matters when I'm doing division. So let's see how this kind of all plays out. Let's take, we've got enough time here, I think, to do this. We had Z1 previously. Let's say Z1 is, I want to go back to one of the questions we did. So that negative 4 root 3, negative 4 root 3 minus 4i. And let's say Z2 was, I think there was one, was it negative 1 plus root 3i? We had that one. Let's do the product. Let's take Z1 times Z2. Let's do it in rectangular form. So I have negative 4 root 3 minus 4i times negative 1 plus root 3 times I. You guys remember how we have to multiply that? What process do we use to multiply that stuff out? I got to distribute, right? And it's binomial times binomial, so it's FOIL. Okay? So let's take negative 4 root 3 times negative 1 gives me 4 root 3, right? So that's first times first. Let's go outside times outside. So negative 4 root 3 times root 3, so it gives me negative 4 times 3, correct? Now I'm going to do inside times inside, so negative 4i times negative 1 gives me positive 4i, right? And then last times last is going to give me negative 4 root 3. What's I times I? Good. So I squared is going to change to a negative 1, right? And I make that positive. So now I have 8 root 3s. Okay, 8 root 3s. And I messed something up here when I took negative 4 root 3 times radical 3i. That's 4 times 3i. So I need an I there. So it's negative 12i plus 4i is negative 8i. Does that make sense? Your O's and I's will always both have an I with them when you FOIL two complex numbers. Is that something we can do? Remember doing that stuff? Okay. Now, let's see if there's a quicker way. Previously, we have already found Z1 to be, Z1 was 8 cis 210. Z2, we found to be 2 cis 120. What this theorem says is that Z1 times Z2 should be R1 times R2. So R1 times R2 is 8 times 2. Which should be 16. Cis now should be 210 times 120. Or sorry, 210 plus 120. What's 210 plus 120? 330. So that is the polar form of Z1, Z2. Does that make sense? Now, if I do want it in rectangular, because a lot of times, if they ask me to multiply two complex numbers, they'll give them to me in complex form. They'll give me to me in rectangular form, A plus BI. I will convert them to polar to do the math, but then I'll present my answer in rectangular again. Does that make sense? So this is going to be actually 16 times cosine of 330 plus 16i sine of 330. Does that make sense? That's r cis of 330, and I just multiplied it out. What's cosine of 330? From that 330 degrees, it's about right there on the unit circle. So the cosine value is radical 3 over 2. So we get 16 times radical 3 over 2, plus then 16I. What's the sine of 330? Negative 1/2. What's going to happen to 16s and the 2's? Cancel, right? Gives me 8 radical 3. 16 and the 2 cancel. Gives me negative 8I. Is that the exact same thing we found up there? Okay. So here's the idea then, guys. I don't know if you were to time yourself on these, if I was to do the stuff in blue, time myself on how long that took, and then do everything that's in red here, including converting those things from negative 4 root 3 minus 4I to 8 cis 210 and negative 1 plus radical 3I to 2 cis 120. I'm going to say that the stuff in red probably takes longer. Okay? However, when we are maybe multiplying 3 or 4 or 5 things together, or I'm taking negative 4 root 3 minus 4I raised to the 10th power. The red stuff is going to be so much quicker than the blue stuff. Does that make sense? Okay. Also, just think about dividing these things. You guys remember how I need to divide? Like, let's say I have that fraction right there. If I needed to divide those, I need to multiply by the conjugate of negative 1 minus radical 3I to the top and bottom there, right? And then I'd FOIL the top, FOIL the bottom, and then start dividing. Well, here, if I want to divide down here, let's go Z1 divided by Z2. So it's 8 divided by 2, R1 divided by R2, and now it's cis. It'll be the difference in here. What's the difference between 210 and 120? 90. So it gives me 4 cosine 90. What's cosine of 90? 0. So it gives me 4 times 0, which is just 0. And then it's I sine of 90. What's the sine of 90? 1 times the 4. So this just turns into 4I. If you were to do this division here by using our rectangular process of multiplying by a conjugate, you're probably still foiling. Does that make sense? And in polar form, I've already got the answer. Okay? So that's kind of how some of this stuff benefits us algebraically. If we were using, in regards to a lot of circular motion type things, complex numbers and rotation and stuff like that, complex numbers are nice. And if we're going to use a computer program, a lot of times we'll code the program to take the input that we have in rectangular form, take that input, convert it to polar, do all the math inside the program in polar form, and then spit back a rectangular result. Does that make sense? It expedites a lot of the kind of computer processes that when we write software. Okay, we're gonna pick up tomorrow with the more. I sent you an email explaining some homework stuff. Please read that email. I think it's a benefit to you in the way I'm doing it, but I want you to make sure that you read it and you're on the same page with me.